Hello everyone, so welcome to the YouTube channel of YourPedia. Here I am Vinny Sharma, your mentor of mechanical engineering. So as you know, Andhra Pradesh Public Service Commission has announced the vacancies for the AEE, okay, and we have one subject that is process calculation and thermodynamics in it, okay, and that subject is very important from this, if you just see from the mechanical perspective as well as the chemical perspective here, okay. This is a common subject for the mechanical and chemical engineering. So you have to prepare this particular subject, even though this subject is very simple, okay, but for the civil engineering student this is going to be an entire different subject here, okay, because they haven't covered this subject in their curriculum, okay. That is a part till +2 here, okay, till 12th exam. So now in this particular video what we are going to talk here, we are going to talk here about the thermodynamics analysis here, specifically for the open system, okay. Specifically we are going to talk about the open systems here. Just see, now in this case here, if we just see what we have to do, we have to do the two type of analysis for the control volume. First we are going to do the mass analysis, and the second we are going to do the energy analysis here. So this topic is very simple, okay. It is not going to be very difficult here, but if you just see the practical applications in all the devices which we use in the industry, we see the direct applications of this particular part here, okay. Because if we talk about the laws of thermodynamics, here we are having a first law which deals with the conservation of energy, like the Bernoulli's equation which we see in the fluid mechanics, okay. So I can say basically the first law of thermodynamics applications we are going to see and we are going to study in this particular part here while doing the mass analysis as well as the energy analysis here, okay now. So you can understand in this way, the first law of thermodynamics is a broad topic, whereas if we just see the Bernoulli's equation which we cover in the fluid mechanics, it is a sub part of a first law of thermodynamics here, okay now, just remember that part. Now first of all, if we talk about thermodynamics here, what does the thermodynamics deals with? Thermodynamics deals with the energy interaction which are taking place between the system and surrounding. So there are different ways of doing the energy interaction. Either we may have the mass interaction here, either we may have work interaction or the heat interaction here. So there are different form of interaction which can take place between the system and surrounding, that we have to understand. The first one is a mass interaction, then we are having a work interaction, and then we are having a heat interaction, okay. Remember this part. Now whenever we are dealing with a different type of system, because in thermodynamics we are having an open system, we are having a closed system as well as an isolated system here, and all the practical devices which we use in the industry are considered as an open system, okay. Now what is the meaning of system? First, system is defined as anything on which our attention is focused, okay. So let us suppose if you are analyzing the simple any pump, any compressor, any machine, or even a simple glass of water, okay, anything which you are analyzing or which you are on which your attention is focused, it is going to be considered as a system, okay. Remember that part. Now if we classify the system, there are three different ways. We are having a system as, I can say, open system, then we may have a simple closed system, and then we may have an isolated system here. In all the cases here, in all the systems here, the classification is being done on the basis of whether the mass interaction is taking place or whether the work or heat interaction is taking place. For example, if we talk about the open system, in that case the mass can flow into the system and out of the system. For example, if we just see a pump, if we just see a practical example of a pump here, in the pump what is happening, the water is entering into the pump at position number 1 with some mass flow rate, and it is exiting from the pump with some mass flow rate from the point number 2. So I can say it is going to be considered as an open system, okay. Similarly, if you are having a closed system, what is the meaning of closed system? Now let us suppose if you are having a water bottle, a simple water bottle is there which is closed from the top, it is closed. Now if you are putting any liquid inside this water bottle at a temperature of 80 degrees Celsius, let us suppose, then what will happen? The heat will transfer from the water and it flows toward the surrounding here from the surface itself. So I can say in this case the mass cannot change inside the system here, but correspondingly heat may transfer, okay. So I can say the closed systems are those systems in which there is no mass interaction, only the energy interaction is taking place. So we have to remember the mass interaction as well as the heat and work interaction both will take place in the case of open system, and in the case of closed system there is no mass interaction but only the energy interaction is taking place. Okay, remember that part. Now in the case of an isolated system, what is happening? Neither the mass transfer take place nor the energy interaction take place. Okay, so there won't be any energy interaction inside the isolated system. So you can say in the case of an isolated system, the total energy is going to be remain conserved. Okay, the energy is not flowing into the system from some external source here, and neither the energy is flowing out of this system here. Okay, remember this case. For example, our universe, so that is going to be considered an isolated system. Now majority of the system are going to be considered as an open system. Okay, like we use the pump, compressor. Okay, pump ho gaya, compressor, we are having a turbines, boilers, heat exchangers. All of these practical applications are nothing but these are the open systems here. So we have to analyze the first law of thermodynamics for the open system now. Okay, now the next part is what is the meaning of first law of thermodynamics. So if we talk about the first law of thermodynamics here, it simply tells you quantity wise the total energy is going to remain conserved in a system here. Okay, the energy does not change, quantity wise the energy is going to be remain conserved. Okay, now that is a simple fundamental. Now just see what are our objective in today's class. So we have to first develop the conservation of mass principle. Okay, then we have to apply the conservation of mass principle to the various system, including the steady as well as the unsteady flow control volumes here. Next, we have to apply the first law of thermodynamics to write down the conservation of energy in the case of open systems here. So these are going to be our objective which we have to see in this particular part here. Okay, now let us move toward the first part. So here we are going to talk about the conservation of mass principle first. Okay, now just see what does the conservation of mass states at. So it is a similar topic which we have seen in the fluid mechanics with the name of continuity equation here. The mass flow rate at the inlet and at the outlet is going to be remain same. That is a simple fundamental. Now if we talk about the conservation of mass principle, so let us say we are having some container. This container is consisting of some mass here. Okay, now what is happening? Now there are two openings, two pipes are connected here. From pipe number 1 the fluid is entering into the container, and from pipe number 2 fluid is exiting from the container here. Okay, some mass is getting in from the pipe number 1 and some mass is getting out from the pipe number 2. That is simply happening here. Okay, now just see we have to apply the conservation of mass principle. So first of all, whenever you are dealing with any system in which the mass conservation in which we have to apply the first law of thermodynamics, and that system is an open system, or in which when there is a mass flow rate into the system or out of the system, in that case we have to define a fixed region in the space. Okay, so there we have to define a fixed region in the space. Now let us say we have defined a fixed region as this one here. Now you can see, now anything which is going to happen inside this green color box, we are going to analyze that. Okay, so that green color region is specifically known as the control volume. So control volume is very important part. It is very important to define here whenever we are doing the analysis of a control volume, whenever we are doing the analysis of an open system here. Just remember that part. Now in this case what is happening? So for the analysis of open system, the analysis is being done by considering the fixed region in the space which is known as the control volume. Now what does the conservation of mass principle states that? Conservation of mass principle simply states that the net mass transfer which is entering into the control volume, okay, and the net mass transfer which is exiting out of this system, okay, from the control volume, it is going to be equal to the net change in the total mass within the control volume. Now what is the meaning of that? What is the meaning of that? Just try to understand it with the numerical values here. For example, let us say I am assuming that initially we are having a mass flow rate, initially we are having a mass inside the container of 10 kg here. So initially we are having a mass of 10 kg. Now what is happening? Mass is getting entered into the system with some mass flow rate. So I am assuming the mass is getting entered the mass is getting entered with a mass flow rate of 2 kg per second here. Okay, along with that, mass is getting exit from the system with a mass flow rate of 1 kg per second here. Okay, now if I ask you what will be the net mass flow rate into the system and out of the system is, so you can simply say, sir, 2 kg per second is getting entered into the system and 1 kg per second is getting exiting from the system here. So that means the net rate with which the fluid is entering into the system, it is equivalent to 2 minus 1 kg per second. 2 minus 1 kg per second. Okay. So I can say the net mass which is getting entered into the system, it is going to be equivalent to 1 kilogram per second. So correspondingly inside the system, the mass is continuously accumulating here and the mass is getting changed. Okay, so you are going to see after some interval of time, the mass inside the volume, mass inside this open system is going to continuously change here. Okay, so if I want to write down the conservation of the mass principle here, so I can simply write the mass which is getting entered into the system minus the mass which is getting out from the system, it is equivalent to 1 kilogram per second. So it is simply representing you the rate by which the mass inside the container is changing here. Okay, now so you can see the net mass transfer to and from a control volume is equal to the net change in the total mass within the control volume during the delta T here. Okay, so that is the first equation. Now, so you can say this is a representation in the form of rate form. So this is representing you the value of 1 kilogram per second here. So per second, how much mass is changing here? By 1 kg, the mass is continuously changing inside the control volume. Okay, now. So here you can see. Okay, now just see. So now in this case here, we have assumed that mass flow rate at the inlet and at the outlet are getting same here, are getting different here, and correspondingly mass inside the control volume is changing continuously with respect to time here. Okay, now just see the next part. Now whenever we deal with the first law of thermodynamics or first law of thermodynamics here, specifically for the open system, okay, there are two different conditions here. The first condition is the steady flow and the second condition is the unsteady flow here. Now what is the meaning of steady flow? Steady flow processes simply means the system, the mass flow rate entering the system and exiting the system are not going to be changed here. That means the mass inside the control volume is not changing with respect to time here. But if the mass inside the control volume and the energy inside the control volume is changing with respect to time, that means we are dealing with the unsteady state problem here. Okay, so here you can see the mass inside the control volume is continuously changing with a rate of 1 kilogram per second. That means we are dealing with the unsteady flow. Okay, but in this case, if you just see this particular diagram, at position number 1 the mass flow rate is 2 kilogram per second. At position number 2 the mass flow rate is the 3 kilogram per second. So I can see the total mass entered inside the system, it is equivalent to 5 kilogram per second, and similarly the fluid is exiting from the system with a mass flow rate of 5 kilogram per second here. So correspondingly you are going to observe the net mass change inside the control volume is going to get 0 here. Okay, so mass inside the control volume is not changing at all. Therefore, I can say we are dealing with the steady flow processes. So remember that if you want to write down the mass flow rate or if you want to do the conservation of mass principle for the steady flow process, that is having a simple formula that total mass which is being entered inside the system, it must be equivalent to the total mass exit from the system here. Remember this condition, and correspondingly the rate of change of mass inside the control volume with respect to time, it must be equivalent to 0 there. Okay, now so that is important for you. Now the next thing, okay, now if we talk about the unsteady flow, so unsteady for the unsteady flow process we have already seen that the mass inside the control volume is going to get changed, and the corresponding equation in this Summation form can be written as net mass in minus net mass out, it must be equivalent to rate of change of mass with respect to control volume here. Okay, so there are different forms of writing the equations, whether you can write in the rate form or whether you can write it for the certain time interval here. Okay, remember that part. Now coming back to the next part here. Now we are going to do the energy analysis. So first part, that is mass analysis, has been done inside the control volume. Now we are going to talk about the energy analysis of a control volume here. So what are the different types of energy, or how the energy can transfer inside the system here? First of all, just see, whenever we talk about the energy analysis here, whenever we talk about the energy analysis, we have to see the different type of energy associated with the fluid. Okay, the first one is, in the case of flow processes, what is the meaning of flow process? The process in which the mass is continuously flowing into the system and out of the system here. That means simply you can say flow processes are representing a case of an open system only. Okay, now just see the important part. When we talk about the energies here, okay, there is a first term which we study, is the enthalpy here. Enthalpy is representing the total energy of a moving fluid which is there due to the fundamental properties like pressure, volume and temperature there. Okay, so it is representing you the total energy of the fluid, total energy of the moving fluid. That is the first thing. So here the enthalpy is basically written as the sum of internal energy and the flow work. Okay, that PV is known as the flow work here. So now just see what I have told you. I have told you that internal enthalpy is representing you the total energy of a moving fluid which is there due to the fundamental properties here. Okay, so here you can see it is a summation of internal energy and the flow work. So why do we have internal energy? Internal energy is representing the energy associated at the molecular level due to the atomic and molecular movement. So whenever you are having a temperature on any particular body here, we are going to see a randomness inside the atom and molecule, and corresponding internal energy will be there. Okay, remember this part. Second, PV. PV is representing the flow work. Okay, PV is known as the flow work here. Actually what happens here, in the case of flow processes, in the case of open system, the work transfer are of two types. The first one is the external work and the second is due to the flow work here. Okay, now what is the meaning of external work and the flow work here? Actually, flow work is representing you the work done which is being there due to the fluid properties like pressure and volume, whereas external work are representing the work done which are crossing the boundary. Okay, so basically these are the boundary phenomena here, but flow work is not a boundary phenomena here. Okay, now so you can see the kind of external work of importance are going to be shaft work or steering work or the electrical work. For example, if you are having some container, in this container if you are having some liquid here, now if you are rotating the liquid with some rod, you are rotating the liquid, at that point of time you are going to experience that we are having the shaft work or steering work here. We are performing the work input into the system, and that comes under the category of a external work. Similarly, let us suppose if I am using any electrical resistance heater to heat up the water here. Now as soon as the current start flowing through the heater, what will happen? The work which is getting entered in the form of electrical work, it is going to get convert into the heat here. That again is crossing the boundary of the system here, and that comes under the category of external work again. Okay, remember this part. Okay, so you can see external work is basically observed on the boundaries here, whereas if we talk about the flow work is due to the fundamental properties like pressure and volume here. Okay, that is a simple thing. So this is a simple expression, this is a simple representation how the flow work is being calculated. So here you can see I have defined a one container. We have a container there in which outlet pipe is given and inlet pipe is given to us. Now what we are doing? We are pushing a liquid inside the control volume, okay, by applying the force P, and the liquid which is being pushed into the control volume or which is getting getting out of, I can say, moving out of the container here, it can be calculated here by, first of all, there I am assuming that I am having some liquid, okay, which is having a pressure P, mass M and the volume V here. Now as soon as you are applying the force F here, but then what is happening? We have applied the pressure over this liquid, due to which it is getting pushed here, okay. So if you want to calculate the value of the total force which we have applied, it can simply be written as pressure multiplied by area. So pressure into area is representing you the total amount of force which you have applied on the piston, okay. And due to this force, what is happening? The liquid is displacing by a length of L here. So I can say the piston is experiencing a displaced volume, okay. So I can correspondingly write the work done which is being done over the system, specifically the flow work, it is going to be equal to force into length, okay. So I can further write this force into length is nothing but it is equivalent to pressure into area into length, where A into L is representing you the displaced volume. And in terms of specific volume, you can write the specific work done will be equal to pressure multiplied by specific volume here, okay. So now you can see the fundamental properties which are there, pressure, volume and temperature, the total energy corresponding to that is representing you the enthalpy, which is a summation of internal energy plus flow work here. So now just here comes the next part. So whenever the liquid is entering inside the container, it is having some it is experiencing some flow work, okay. That is the first thing. Along with that, it is also having some temperature. It is not like that the water is at a 0 Kelvin temperature. We are having a certain value of the temperature also. So due to the temperature, we are going to experience internal energy, okay now. So I can say, as the liquid is getting entered, due to its fundamental property, the energy associated will be internal energy plus the flow work here. And also along with that, the liquid is entering with a certain velocity of let us say c, okay. And if I take a reference here, I can define the potential energy associated due to its position also. So you can see the total energy which is being present at the inlet of the pipe, it is consisting of the microscopic energy which is there due to the fundamental properties, along with the macroscopic energy which is there due to the bulk movement and the bulk position here, okay now. So I can write at point number 1, at the inlet here, the total energy associated will be a sum of U plus PV plus C square by 2 plus GZ here. And similarly you can see at point number 2, at the outlet, we are going to experience this similar type of energy, that means internal energy, flow work, along with some kinetic energy, along with some pressure potential energy here, okay now. So that you have to remember here. So if we want to write down the energy balance equation now for the steady flow process here, in that case, what do we say? Again, we are dealing with the steady flow. Steady flow simply means the properties are not changing with respect to the time inside the control volume, even if it is mass or even if it is energy here, okay. So now you can see during the steady flow process, no intensive or extensive properties within the control volume is not changing with respect to the time here, okay. Or I can write the mass is going to be remain constant, as well as the total energy is going to be remain constant here, okay now. So that is very, very important. So according to the first law of thermodynamics, which deals with the conservation of energy, so let us suppose if you are having a container, now fluid is entering with some energy, let us say E1, and it is leaving with some energy E2. Now you want that the energy inside the system does not change at all. So energy change is not going to experience only when the energy rate at the in and at the outlet, it must when they are equal to each other. In that case, you are not going to experience any energy change inside the control volume, okay. So remember this part. So I can say for the steady flow process here, I can write the energy in it must be equivalent to the energy out here. If the system is not steady flow, okay, in that case the energy inside the control volume may get changed. Why? Because let us suppose the temperature inside the body is changing continuously, okay, so correspondingly internal energy will change. There will be some external energy transfer taking place through the surface here. So there we may have different type of cases here. Okay, so remember that part. In the case of steady flow process, we are going to experience the rate of net energy transfer in, it must be equal to the rate of net transfer exiting from the system here. But if you are dealing with the unsteady flow processes, in that case you are going to experience that the difference is not going to be get zero here. So due to which the energy inside the system is going to continuously change with respect to time here. Okay, now that we have to remember here. So where do we see the applications of this energy analysis here? So as I have already told you that we are in all the practical devices like pressure, like pump, compressor, turbine, boiler, heat exchanger, okay, throttle valve, nozzle and diffuser, there we see the application of a first law of thermodynamics, and there we have to do the energy analysis here. Okay, and in all the cases here the system is going to be considered as an open system, so we have to define the control volume in that case. Okay, just remember that part. Now coming back to the next portion. So how do we write down the energy analysis for an unsteady flow process? We have already seen that in that case energy in and energy out, they are not going to be get same here. Due to this difference here, we are going to experience the change in energy inside the system. Okay, and it is not a necessary condition that this term is going to be positive only. Okay, there may be a chance energy may get increased, there may be a chance energy of the system keep on decreasing here. So energy of the system may have a positive value, it may have a negative value also. Okay, remember that part. Okay, so these are the very simple part here. And where do you see the applications of the unsteady flow processes? Here you can see, let us suppose you are filling the water tank. Okay, you are evacuating the water tank. In that case, the corresponding energy of the system, the mass of the system is continuously changing with respect to time here. So all of these are the example of a unsteady state processes here. Okay, now, so that's a very simple part. Now let us see some questions related to this particular portion here. Okay, just give me a second. Yeah, here you can see this is a general expression. This is a general expression for a unsteady flow. Okay, so here you are going to see this first term is representing you the total energy in here. So total energy in is basically a summation of, just see the individual terms here. What is it representing? First, theta here. Theta is actually representing you the internal energy of the fluid plus flow work here. Okay, so here you can see, let us suppose we are having a container and the fluid is entering here. So at position number 1, the fluid is going to have some particular temperature due to which we are having internal energy. Okay, due to the displacement of volume here, we may have a flow work here. Okay, along with that, due to the bulk movement, we may have a kinetic energy. Due to the bulk position from the reference, we may have a potential energy. Okay, now similarly, there may be a chance that heat may transfer into the system. There may be a chance. Okay, so that's it what we have represented here. So now you can see the mass multiplied by this total this term here representing you the total amount of energy which is getting entered due to with the transfer of some fluid, and this Q and W are representing these corresponding heat transfer and the work transfer which is taking place from the boundary itself. Okay, so they are not there due to the fluid transfer, they are due to the boundary, they are basically the boundary phenomena. And similarly, when the fluid is exiting from the system, when the fluid is exiting from the system at point number 2, it is having some temperature, due to which we are going to experience again the internal energy. It is going to have some flow work at point number 2. Okay, so as it is moving, it is having a bulk motion, so due to which it is having a kinetic energy. Along with that, there may be a energy due to its position also, so we may have a potential energy. Okay, so this is representing you the total amount of energy transfer due to the mass transfer here, or due to the flow of the fluid here. Along with that, there may be a chance heat and work may get transfer from the system in the form of work and heat. Okay, so difference between these two are representing you the total change in this energy inside the control volume here. Okay, now, so that we have to remember. So now you can see applications here: charging of the rigid vessel, whether you are filling the water tank or you are evacuating the any tank here. That is example of a unsteady flow processes here. Okay, chalo. Now let us see some questions related to this particular part here. So this is a very simple part. In the thermodynamic analysis of an open system, what is the fixed region in the space called through which the moving substance flow here? So in the case of an open system, what we have to do, we have to define the fixed region in the space on which our attention is focused, and that fixed region is known as the control volume. Okay, and you have to remember the outer surface of the control volume is known as the control surface. Okay, remember that part. Coming back to the next question, the total energy of a flowing fluid entering or leaving a control volume processes which combination of energy per unit mass? So now just see, when we are talking about the energy of a flowing fluid, just see, we are talking about a energy transfer due to the flowing fluid. We are not taking the consideration of a boundary phenomena here. So you must know that whenever the fluid is flowing, due to the temperature we may have an internal energy, due to the pressure and volume we may have a flow work, due to the bulk movement we may have a kinetic energy, along with that potential energy here. Okay, so you are going to experience the 4 terms: internal energy, flow energy, kinetic energy and the potential energy. Okay, these are the energy associated with the flowing fluid entering or leaving a control volume here. Just remember this part. Next question. A steady flow turbine in a power plant receive high pressure steam and reject it at a low pressure to produce the shaft work. If the kinetic and potential energy changes are negligible, how does the steady flow energy equation simplify to express the work output per unit mass relative to the fluid properties entering 1 and 2? Okay, now what is given to us? So we have been provided with the turbine here, let us say like this one. Now the fluid is entering at point number 1 with some particular energy. Okay, now we know. Now let us say the energy at the inlet is represented by energy in. Similarly, the fluid is entering with some energy at point number 2, which is represented by energy out. Okay, and there is no heat transfer taking place due to the from the boundary here. So I am assuming that there is no heat transfer. So this Q is basically equivalent to 0. Along with that, turbine has a sole purpose to produce the work here. So I am assuming the work is being produced from the boundary itself. Okay. Now, according to the steady flow energy equation, we are talking about a steady flow. What is the meaning of steady flow? Energy which is getting entered into the system, the total energy, it must be equivalent to the energy out here. I am talking about total out energy here. Okay, so here you can see total energy entered, it is equivalent to energy in plus this Q, but there is no heat transfer taking place, so this Q is going to be 0. Now the total energy getting out from the system, it is equivalent to E out plus energy is also getting rejected in the form of work also here. Okay na? So this E in and E out is representing the energy associated with the moving fluid. So now you can see energy in is represented as internal energy plus flow work. Okay, due to its bulk position, bulk movement, we are having a kinetic energy, plus due to its position we may have a potential energy. Energy out, similarly at the exit here, it will be equivalent to U2 plus P2 V2 plus C2 square upon 2 plus GZ2 plus work here. This is the expression you are going to see. So now just read the question. First, kinetic and potential energy are negligible here. So I can write C1 and C2 change will be 0, potential energy change will be 0. So I can further write here that W will come out to be as U1 minus U2 plus P1 V1 minus P2 V2 here, and the summation of U1 and P1 V1 is representing you the enthalpy. Okay, so always remember that the expansion of the steam in a turbine, it is represented as a adiabatic process here, isentropic process here. So I can write the work which is getting out from the system, it is equivalent to the change in enthalpy here. Okay, now it is not going to have only internal energy and the flow work, both will be there, both may get changed. But if the temperature at point number 1, if the temperature at point number 2, both are same, at that point of time you can see the work output is going to be equivalent to the option number C here. Okay, sorry, option number, this second term is representing the work output here if the temperature is not changing at all. But in the case of steam turbine, the pressure and temperature both changes, due to which it is always represented with the change in enthalpy. Okay, now next part, an engineer is analyzing a steady flow compressor used to pressurize air. So we are analyzing a steady flow compressor here. During a test, it is observed that total rate of mass entering the compressor is 2.5 kilogram per second. If there are no leak in the casing, what must be the mass flow rate of the air leaving the exit here? So that's a very simple question here. So now you can observe here, if we talk about the conservation of mass principle, the mass which is getting entered into the system, it is going to be equivalent to the mass exit from the system. So now you can see if the mass in is 2.5, then the exactly 2.5 kilogram of mass is going to be out from the system here. Okay, now next part, consider the unsteady flow process here of inflating a car tire from a completely flat state using a pressurized service line. So basically what we are doing here, we are filling the air in the tire. So initially it is having a 0 air, okay, the volume is 0, then we are filling it with the pressurized service line. Which of the following correctly describe the mass balance of the tire control volume during this charging process? So what is going to happen here? You are entering the mass inside the system. So first, how do we write the conservation of mass principle for the unsteady processes? Mass in minus mass out, it is equivalent to the rate of change of mass inside the control volume here. We can write in this way. In the case of car tire, there is no mass transfer from the system. There is no mass leakages is taking place. So I can say all the mass which is getting entered into the system, it is going to increase the mass inside the control volume. Okay, now so now you can see option number B is going to be the correct answer. Summation of mass in is going to be equivalent to rate of change of mass inside the control volume, because there is no mass leaving the tire. Okay, now next part, in a refrigeration system, the refrigerant passes through a throttling valve, which is a steady flow energy device. Assuming that device is perfectly insulated and does not produce any shear, shaft or electrical work, what happens to the enthalpy of the fluid crossing the valve? So that's a simple question. In the case of a throttling process, we must know that the enthalpy is going to be remain constant. In the case of throttling process, there won't be any change in the I can say change in kinetic energy, there is no change in potential energy, and the corresponding heat and work transfer are also 0. So if you apply the steady flow energy equation, you are going to experience the enthalpy is going to be remain constant. Okay, so option number C will be the correct answer in this case. Enthalpy is going to be remain approximately constant here. Okay, So these are the few questions related to this particular topic, conservation of mass and energy. So that is a very simple topic here. You must be clear that how to apply this principle in the case of open system, closed system and the isolated system. So today we have talked about the open systems here, and that is the only topic which we have to cover in this part. You don't have to do this mass analysis in the case of closed system and the isolated system, because there the mass always remain constant. Okay now. So I hope this is very clear to all of you. So that's a simple topic. Okay. Now in the next video we are going to see some other part here of this particular subject, that is process calculation and thermodynamics here. Okay now. So thank you very much.